All right, so this week we are going to finish up chapter 4. So we're going to do 4.3 and 4.4. There's 2 lessons. We've got 3 days to do them, and then we also have a review day built in on Thursday. So what we're going to be looking at is solving equations, mostly algebraically. We'll do the first one graphically, so you will need your calculators for that one. But we're mostly going to focus on algebra. So what do the equations look like that we're going to solve? Well, they're all going to have rational expressions in them. Okay, that means that they're going to have fractions. So an example of something that we'll be solving would be like that. Okay, we're a ways away from doing this, but that's the kind of problems we're going to look at. And the only thing that's really making that problem hard is the fact that it's all fractions. So the approach we're going to take is, can we somehow get rid of all these fractions before we even have to really start doing algebra, right? And if we can, it's going to make it a lot easier to solve. All right. So the first problem that we're going to do, it's going to be a word problem, and it's going to involve distance, speed, or rate, and time. If you didn't know the formula that I put up on the board, we are going to need that formula to do this, and we're going to use that in homework as well. So that's the distance equals rate times time formula. So it's a formula that relates how far you've gone based on the speed that you're traveling at and the amount of time you've been traveling. Now, one thing we are going to have to do with that formula is rearrange it. So right now it's arranged so the letter D is by itself on the left. I'd like to rewrite it so the letter T is by itself. So if I have this, what could I do on both sides that would get the T by itself? Remember, there's a times sign right in there.
Divided by R.
Yeah, I could divide each side by R. And now that gives me a formula for time. It says distance divided by rate gives us time. Okay, so it's the same formula, but that's the arrangement we're going to have to work with in this problem, because it's going to be a question about time. So here's the problem situation. What's happening in this problem is Sue is traveling somewhere, and she's going to take 2 different modes of transportation to get where she's going. She's going to drive for part of the trip, and then she's going to get out of her car, get on the train, and take the train the rest of the way. So let's just read what they tell us. It says that Sue drove 30 miles. That's by car. She drove 30 miles by car to a train. From there, she got on the train. And in all, the entire trip, including what she drove and the amount she went on the train for, was 120 miles. That's the whole trip. We don't know how fast either the train or the car was going, but we do know the train, on average, was 20 miles an hour faster than the car. And of course, all these speeds can change because you may never drive at a exactly constant speed the whole time. That's why we're dealing with average speeds. Okay, average. All right. So what they want us to do is find a formula for the amount of time it takes to complete the trip. And they want us to do it in terms of the speed of the car. So when I'm done, I'm going to have a formula that if you tell me the speed of the car was 40 miles an hour, I could plug the number 40 into this formula, and it'll give me a number that says 3.4 hours or something. Plugging in a number will tell me how long it takes to do the trip. And it's going to take into account all this information. The length of the trip in miles and the speed of the car and the train. Okay, so first of all, rather than writing a formula like in math, I want to write this out as like a sentence, okay, what we're looking for. We're trying to find the total time it's going to take Sue to do this trip. How many different modes of transportation is she taking in this problem? Two. So what's the first mode of transportation?
Train. Or car.
Yeah, if we just read it the way it, in the order it's written. It says she drove 30 miles to the train station. So the first thing we have to do is figure out how much time she spends driving. Okay, that's going to be part of the total time. Now, is the time she spends driving the car, is that the whole trip? No, there's another part to the trip. All right, so we got to figure out the time that she's in the car. And what else do we have to figure out besides just the time that she's in the car?
Time in the train.
Right, the time that she's in the train. And to find the total time, we're going to take the time she's in the car, the time she's riding on the train, and what are we going to do with the car and the train time? We're going to add them. Okay, so that's the first step. There's really no math there. It's more of just kind of a big picture. What are we trying to figure out? Now we got to start putting in some symbols and figuring stuff out. They didn't tell us the amount of time she spends in the car, but we have a way to figure out how much time she spends in the car if we take how far she drove in the car and divide by the speed of the car. So if we take those two things and divide them, then we'll have the time in the car. What is the distance that she traveled by car?
30 miles.
Okay, so she traveled 30 miles. And now if you take distance and you divide by speed, you get time. What's the speed of the car in this problem? It's true, we don't know it, but we have a way to represent it.
20
X. X is the speed of the car. So now if you take the distance the car traveled divided by the speed of the car, there's your time in the car. Okay. Now we need the time on the train. Okay, it's the same idea. We don't know how much time she spent on the train, but if we take the distance she travels on the train, divide by the speed of the train, that'll give you the time on the train. What's the distance that she traveled by train?
90 miles.
90. Right? They didn't give us that, but we can figure it out because we know the whole trip is 120. She did 30 of it by car, so that means she did the rest by train. So she did 90 miles. That's the distance on the train. And now divide that by the speed of the train. What is the speed of the train? We do not have an exact number. We only have the speed relative to the car. Yeah?
Would it be X plus 20?
Right, it's 20 miles per hour faster than the car. That's all we know. And that's the time as a function of the speed of the car. So I'm going to call the formula. Sometimes you use f of x, g of x. I'm using t of x because it's time. That's it. So now if you told me the car was going 40 miles an hour, I fill in 40 for x, and the answer I get will be the speed, the amount of time it takes to do the trip. In this problem, they're not actually asking us to fill anything in. They just said find a formula, find an expression. Hey, any question how we got that? So that's our formula. So now we're going to do a few things with that formula. We're going to forget that this formula is part of a word problem for a minute. Because when we're dealing with it as a word problem, there are restrictions on the letters that might not be there if it wasn't a word problem. For example, x is the speed of the car. The speed can't go lower than what number? Yeah, you can't go lower than 0 miles an hour. Algebraically, you can let x be any number you want, except what would cause you to divide by 0. So we're going to forget that this is about a word problem for a minute, and just find the things that they want to know based on this math equation. Okay. Now, some of the things that they're going to ask us to find, we can only really do it if these two fractions are put together as one. Some of the things we could leave that the way it is and do it, but some we can't. The EBM is one of the things that we can't do unless those two fractions are together. To add two fractions together, what do you have to make sure that you have?
Same number.
You have to have the same denominator. So if you had something like this, again, this is just an example I'm making up with numbers, and then we're going to extend it to the one we're doing. What's the common denominator between 5 and 7 if you wanted to add those up?
35.
It's 35. And the way you find that is you just multiply your two denominators together, and you put the product of those two numbers in the bottom. When they're numbers, you could actually put them together and write 35. When they're letters, you can't. We just have to leave it as the first denominator times the second. So let's start with that. There's our common denominator. Now, to make sure that each fraction has the common denominator, you multiply the top and the bottom by something. What would you have to multiply the 3 and the 5 by to make it have the common denominator? 7. And what would you have to multiply the 4 and the 7 by? 5. So you multiply each fraction in black by the other denominator. So 3/5 gets multiplied by the 7, and the 4/7 gets multiplied by the 5. Okay, we're going to do exactly the same thing in this one. So we're going to multiply top and bottom by what here?
X plus 20.
The other denominator, x plus 20. Top, bottom. And what are we going to multiply top and bottom by
X.
in this one? Yep, the other denominator, x, x. Now, when we have numbers, we just do it out. 21 plus 20, and we write down our answer. When we have letters, sometimes we, like this one, we have to distribute. 30 times x is how much?
30x.
I'm just going to put that up here for a second. 30x. And what's 30 times 20?
600.
600. Okay, so that's that part. And now I have, that's positive 90 times x. That's 90x. And you're adding together. That's going to be my numerator. What's 30x plus 90x?
120.
120x. And then the 600, I don't have anything to combine it with. So what I had on the left and what I have on the right, they're the same thing, except now it's all together as one fraction. Before it was 2. All right, now let me show you why we put it all together as 1. Let's find the EBM. To find the EBM, you take the highest degree term in the top and you divide by the highest degree term in the bottom. In order to have a highest degree term, you have to have a single fraction. You can't have two separate ones. So now look at this. Okay. What's the highest degree term that's in the top?
X.
Over 1.
So not the degree of the term, the actual term itself.
120x.
120x. Because what's the, now this is a separate question. What is the degree of 120x? 1. Yeah, the highest exponent in that is a 1. The other term in the top is a 600. What's the degree on that one?
Zero.
That's a degree 0 because it doesn't have a variable. Yep. So we're picking the term with the higher degree. That's the 120x. Now you're going to be a little careful about the bottom. What would be the highest degree term in the bottom if that was all multiplied out?
X2.
It would be x to the second. You'd have an x to the second, and you'd have a plus 20x. The one with the highest degree is x to the second. Now that reduces a little bit. What can you cancel from the top and the bottom? 1x. And what does that leave you with? 120 over x. Okay, so there's your EDM. Now, the EBM is also used to give us the horizontal asymptote. To find the horizontal asymptote, you let what I just circled get really, really big, and you tell me what's going to happen to what's in this box. Okay?
Small.
It gets really small, right? As x gets really, really, really big, the bottom of the fraction gets really, really, really big. If the bottom of a fraction gets big, the whole fraction gets small. And it's going to get so small that it's going to get close to what number?
0.
0. So your horizontal asymptote is at 0. Anytime the EDM has an x in the bottom, when it's completely reduced, it's always a horizontal asymptote of 0. Now, since it's horizontal, what letter should we put on the left side?
X. Or
Y.
Y. If we put x, what kind of asymptote would that be?
Vertical.
That would be a vertical. We're going to do that next. Okay, here's your horizontal asymptote. Those are the only two things that you had to combine those together to do. Everything else you pretty much could have done the way it was. Okay. Let's look at the vertical asymptotes. Okay. The vertical asymptotes are the numbers that would cause you to divide by what? 0. And in this case, there are two numbers that would cause you to divide by 0. You can either look at the one thing. You can look at the one that we combined together or the one we left separate. Does anybody see a number you could plug in for x and it would cause you to divide by 0? 0, yes. If you plug in 0 right there, it causes you to divide by 0. Somebody remind me again, how do we write a vertical asymptote?
X equals.
X equals, first one is 0. How about another number you could plug into the denominator and you divide by 0? Negative 20. Now, you might be thinking, wait a minute, how could x be negative 20? X is the speed of the car. We're forgetting it's about a word problem. Okay? So we're just answering the questions they wanted us to answer. So x is negative 20. Okay, so we got our EBM, we got our horizontals, we got our verticals, and they also want to know the zeros. Okay, so remember what a 0 is. That's a number you plug in, and when you do, it causes you to get an answer of 0. Okay, I think the easiest way to figure out the zeros is look at the fraction that we combined together. Set that equal to 0. And that's what we're looking for. Okay, we're trying to solve that fraction. So think about a fraction equaling 0. How can you divide two things and have it come out to 0? There's only one way that can happen.
Put 0 in the numerator.
You have to have a 0 in the numerator. That is the only way you can divide two things and get 0. The top has to be 0. It doesn't matter about the bottom. Well, the bottom can't be 0, but you need to make the top 0. Okay. That's how you find the zeros. So take 120x plus 600, that's the top, and tell me what would make the top 0. Okay, and that'll tell you where it crosses the x-axis, because that's what we're trying to find. The zeros are the x-intercepts. Okay, what would be my first step to solve that equation for x? Minus 600. And now divide by 120. To make that a little easier to think about in our head, we could cross the zeros off. 12 divided by 12, that's gone. What's negative 60 divided by 12? Negative 5. That's where this graph crosses the x-axis. And if you plug negative 5 into the numerator, you will get 0. You'll have 0 divided by something that's not 0. And I know the bottom wouldn't be 0 if I plug in negative 5, because I already found the two numbers that make the bottom 0. Negative 5 wasn't one of them. All right, so I think that's everything. So let's last step is just find a complete graph. So keep in mind your vertical asymptote is at negative 20, so I'd probably go back to, let's go a little more, let's go like negative 40, just so we can see the whole graph. Okay, oops, which version of the problem you type in, it doesn't really matter. I'm going to do the second one because it's all one fraction rather than two, and I won't need as many parentheses. Okay, so we're going to still need parentheses around the top. Divided by, and I'm going to do the bottom out so I don't have to put an extra set of parentheses around x plus 20. What would you get if you multiply that x out?
X to the power of 2.
X to the power of 2
Plus 20.
plus 20x. Yep. That's the simplest way I can type it in that I know of. Okay, so we're going to set x min, I'm going to say negative, let's do negative 40. X max, I don't know, let's do positive 60. Okay, y min and max. Well, I'm going to leave the y max at 10, but I'm going to set the y min a little lower. Let's do negative 30. Since there are two vertical asymptotes, that breaks the graph into 3 sections. Because every time you put a vertical asymptote, it's going to break it. So one vertical asymptote would break it in half, and then another one would break it into thirds. So let's see. Let me just make sure I typed in everything right, because that doesn't look super. 120x plus 600. Oh yeah, what did I do wrong?
You multiplied.
Yeah, I multiplied. Forgot my divide by sign. That will make a big difference. Okay, so there's the left part of the graph. There's the middle part, and there's the right part. So there's your 3 pieces. Yes.
How did you move over like the whole thing to the right? Because I always have to like retype in the whole thing.
So I press second, and then I press insert.
Oh, okay.
Second delete. So like if I do that, now instead of typing a number over the 1, it's going to add a number in front of the 1. Yeah.
That's amazing. Okay.
Yeah. When your cursor's blinking and it's a black square, that means it's going to change the number that it's over. When you press second insert, now it's blinking, but it's not the black square anymore. It's going to add numbers in front of it, and it'll keep adding numbers until you move the cursor. Now it's going to start typing over them again.
Okay.
Yeah. Okay, so let me hit graph on that one more time. Okay, so we got our graph. That looks good. I can see I got 2 vertical asymptotes. One there, one at negative 20, and I have a horizontal. Now, out of the 3 parts, let's call this one on the left part 1, the middle is part 2, and the right is part 3. Which part of the graph would actually represent our word problem? Part 1, 2, or 3? Which one?
3.
Yeah. Because when dealing with the word problem, negative values of x wouldn't make sense. Can't have negative speed. You also can't have negative time. So when we start to just focus on the word problem, that's part 3. That's the part that was in the upper right. The x-axis is speed, and the y-axis is time. What do you notice about your time as you travel further to the right? It's what?
It's like a longer process, or like more time.
So as you head to the right on this graph, what's happening to your time? Yeah.
You save less time the faster you go.
Yeah, you save more time the faster you go, because you're going faster. The amount of time is starting to get lower, but the amount of time will never reach what number?
0.
It can't reach 0, okay, because it's impossible to get from one point to the other instantaneously. Right? Unless you're watching this in the future, maybe we figured that out. But as of right now, you can't instantaneously travel. So it'll get lower and lower and lower towards 0, but it'll never reach it. All right, so now, using that graph, it says Sue has 2 hours to complete the trip. Find out what speed she has to travel by car. All right, and let's say she wants to make the trip in exactly 2 hours. How am I going to mark 2 hours on that graph? Yep.
Is that the second y value?
Okay, yep. So how am I gotta mark that somehow on the calculator?
Would you just make it a line?
Yeah, how would I do that?
Oh, just put in 2.
Yeah, just go to y equals and put a line in at 2, and that's gonna give me a mark at 2 hours. So right there is exactly the time for 2 hours. Well, I can't really tell where that is. So what do you think I'm gonna do now?
Zoom in and find the intersection.
Do the intercept one?
Yep, we're gonna do second calc, do the intersect. The only thing you have to make sure of is that the intersection point is on the screen. If it was off the screen, you'd have to zoom further to the right. Mine's definitely on the screen. I think I went up to 60 miles an hour, so it's slower than 60. Okay, does the guess matter? No, because there's only one intersection point. Okay. So if Sue is going to complete the trip in exactly 2 hours, it says to find the speed of the car. Okay, so what would be the speed of the car in this problem? How much is it?
46 and a half.
Yeah, it's about, we'll go to 2 decimal places, 46.46. Okay, that is the speed of the car. Now, what if it said find the speed of the train? What would the speed of the train be?
Add 20.
Right, we'd have to look back at the original problem, and that said the train is 20 miles an hour faster than the car, so that'd be 66.46. So when you get to that final step, just read the question and make sure you're writing down what they want. Okay, in this case, they wanted the car. So I wrote we were going to do it algebraically and graphically, but we're going to do a lot of other ones algebraically, which is why I just did it graphically. Okay. Any questions on that one? All right. So if we go back and look at the equation, what do you notice about all the denominators in my equation? They all have letters in them, right? And I said that the approach we were going to take is to try to get rid of your denominators. Well, they all have divided by and they have a letter. What's the opposite of dividing? Multiplying. So if you want to get rid of a denominator, you need to multiply. The problem is there's letters in the bottom. If you're solving algebraically and you try to get rid of something by multiplying and it has a letter, that can mess up our problem. So we need to talk about what could happen and what do we do, okay, if that happens. All right, I'm just going to reword this a little bit. So we didn't actually do it in example 3. I'm just going to write down what could happen, and then we'll do it in the next problem. So when solving algebraically, if, and this doesn't happen in every math equation, not every equation is fractions with letters in the bottom. If you don't have fractions with letters in the bottom, what I'm writing right now doesn't matter. Okay, but we are going to have fractions with letters in the bottom, just like that. Okay, so when solving algebraically, if you multiply both sides of an equation by actually I'm just going to go like this, and then I think I can just move the rest up. By a variable, comma, this may result in an equation not equivalent to the original.
Sorry, guys.
Okay, so just put all that together. So when solving algebraically, if you multiply both sides of an equation by something with a letter in it, this can result in an equation that's not equal to what you started with. What that means is we may solve it and get something that shouldn't be there. And there's nothing we can do to avoid that because of the method we're using to solve it. Anytime you multiply both sides by a letter, you can get an extra answer in the problem that shouldn't be there. But that's how you have to do it. That extra answer that shouldn't be there is called extraneous. An extraneous answer is an answer that you created that shouldn't be there because you multiplied both sides by a variable. So in other words, that extra answer works in the problem that you made by multiplying both sides by a variable, but it doesn't work in the original problem before you did that. And the answer has to work in the original problem. So how do we know that the answer doesn't work? We have to check it. Okay, so we plug it back in, see if it works. If it doesn't, it's extraneous. So we're going to go through, we're going to try a couple problems. I'll do one where we get some answers that work and some that don't. So you can see how you tell which ones are the good answers and which ones are the ones that are not the answer. Okay. Everybody have that. Let me leave that up then. So first, I want to just look at a problem without letters in the bottom, okay, to kind of get an idea of how we're going to do this. Let's say you had an equation like this. So you had, and again, this is not the one that we're going to do in a minute. I'm just making up a simple x over 3 plus 2/5 equals 4x over 15. The only thing that's making that equation a little harder to solve than like a normal equation is it has all fractions. If we could figure out what to multiply that, and that by, so all the fractions disappear, then this problem gets a lot easier. Now there's no variables in the bottom. Okay, I'm intentionally picking something that's a little easier. So this extraneous thing isn't going to happen in this problem. What you want to do is multiply the first, second, and third fraction by the LCD. Okay, that's the least common denominator. That is a number that 3, 5, and 15 all divide into evenly. So an example would be 30. But that's not the least common denominator. Does anybody see a number smaller than that? That 3, 5, and 15 all go into 15. Now, you'll see why I'm going to do this in a second. I'm not going to think of it as 15. I'm going to think of it as 3 times 5. Okay. And you'll see why when we start doing it with letters. I'm going to multiply this first one by 3 times 5. I'm going to multiply the second one by 3 times 5. I'm going to multiply the third one by 3 times 5. When you do that, something's going to cancel out in each fraction. Okay, let's look at the first one. We've got x divided by 3 times 3 times 5. What cancels out in that first calculation? The 3, because you're going to divide by a 3, and then you're going to times by a 3. How about in the second fraction? Right, you're going to divide by a 5, and then you're going to times by a 5. So that's common. How about in the third fraction? The whole thing. You're going to divide by a 15, and you're going to times by a 15. Now, look at what you have left and compare it to what we started with. What's x times 5? 5x. Plus, what's 2 times 3? 6. And what's on the right side? 4x. Look how simple that equation just got compared to what we started with. Done. X is 6. Now, looking at the original problem, that's a lot harder to tell because of all the fractions. Get rid of the fractions, it's a lot easier. Okay, so that's the idea that is really important for the next problem. You end up multiplying all 3 fractions by the denominator that's here and here, as long as those 2 multiply together to give you that one over there. If they don't, then it's a little more complicated. Like if you had something like this, the least common denominator is not 15 now. It's the product of all 3 of those, right? Or that is a denominator. 3 times 5 times 16. So in that case, you'd have to multiply this first one by 3 times 5 times 16. The second one, 3, 5, 16. And the third one, 3, 5, 16. Then it just gets a little bit messier because the numbers get a little bigger. But most of the problems I give you, this number times that number will equal that number. So that eliminates that problem. So what we did in that last problem was to multiply each fraction by the LCD, least common denominator. And technically, it doesn't have to be the least. It could just be a common denominator, but the smaller that you multiply by, the smaller your numbers will be when you're doing your work. Okay, so let's look at this one. The first thing you always want to check is if you multiply this one times that one, do you get that one? If you do, then it makes the problem a lot easier. You just have to multiply all 3 fractions by that times that. So let's multiply those together and see if we get that. Okay. What's x times x? So x squared. What's x times negative 3? Negative 3x minus 1x. That's negative 4x. And what's negative 1 times positive 3? 3. So when I multiply that denominator and that denominator, do I get the one on the right? Okay. Yeah. Okay. So now that should give you a hint at what we're going to multiply everything by. So now we're going to do this. We're going to do this step in red. what is each one of these fractions going to get multiplied by?
X minus 1 times X minus 3.
X minus 1 times x minus 3. Exactly. This is like the 3 times 5 step that we did in the last problem, except now it's not numbers, and we're using letters. We're multiplying both sides by something that has a letter in it, so we could get an extraneous solution. Okay, so we got to check our answer. Okay, x minus 1, x minus 3. X minus 1, x minus 3. X minus 1, x minus 3. Okay. What is going to cancel out in the first fraction?
X minus 1.
Divided by x minus 1 times x minus 1. Yep. What's going to cancel in the second fraction?
X minus 3.
Divide by x minus 3 times x minus 3. And in the third fraction? The whole thing. That times that is that. So now we have to write down what we're left with. Usually what you're left with is some kind of distributive property. What's 2x times x?
2x and
2x squared. And what's 2x times negative 3? Negative 6x. Now this is the part you're going to be careful in the middle. You are distributing this. That's positive 1. That positive goes with the 1. So if that was a negative, you'd be distributing negative 1. What's positive 1 times x?
X.
There's x. And positive 1 times negative 1?
Negative 1.
Negative 1. And what do we have on the right side?
Plus 2.
Just a plus 2. Now, at this step, all your fractions are gone, and we should be able to solve it using things we've already learned. What kind of equation is that? Yep, it's quadratic, because the highest exponent is a 2. When you're solving a quadratic, what do you always get it equal to?
0.
Yep.
0.
Yep, I'm going to get it equal to 0. And then our choice from there will be to factor it or quadratic formula. Okay, so 2x squared. What's negative 6x plus 1x?
Negative 5x.
Negative 5x. And let's bring the 2 over to the other side. So it's equal to 0. What's negative 1 minus 2? Negative 3. Okay. So if you're not sure how to factor it, you could jump right to quadratic formula, but it does factor, and that's faster. What would be my first term in each parenthesis?
2.
And they have to multiply together. They give me 2x squared.
2x and x.
2x and x. Yep. You've got a negative in the middle, and you have a negative constant. What does that mean about your signs?
Plus minus.
Yes, you need a plus and a minus. It does matter which one goes where. I'm just going to try plus minus. If it doesn't work, I'll fix it. Now I need two numbers that are going to multiply to give me 3.
3 and 1.
3 and 1. And it does matter which one goes where. I would try 3 and 1. Let's check it. 2x times x is 2x squared. What's 2x times negative 3?
Negative 6.
Negative 6x. What's 1 times x? Negative 6 plus 1. Perfect. Negative 5. Okay. So factoring it, that's the hard part. Now, what do we do with each one of those factors? Set them to 0. Okay. When you solve the first one, minus 1 and divide by 2. And solve the second one. What do you get there? 3. Now, what do we have to do with both of those answers? We gotta check them, because it is possible that one of them doesn't work. Let's check the 3 first. Look at the original problem. I'm just going to move these off so you can see the denominators. Can we plug 3 back into the original problem? Yeah?
No, because the second will equal 0.
The second fraction will equal 0, and, well, denominator will equal 0. What other fraction would also come out to 0?
The right one?
The right one, yeah. Because this one is a product of these two. So if you plug in 3 here, you'd get 9, take away 12, plus 3. That's 0. So if you try to plug 3 back in, it causes you to divide by 0. You can't use that answer. That is extraneous. It doesn't mean that I don't want that answer. I might still ask you for it. I'll just say, type in the answer, and then tell me if it's extraneous or not. Now, -1/2, that would work fine. Okay? Unless you made a mistake in your math, -1/2 does not cause you to divide by 0, so that answer is good. What would be the other answer that would cause you to divide by 0? 1. So 1 and 3 are the two numbers we were looking out for. If we got a 1 or we got a 3, after we did all our work, we need to cross those answers out. And we got a 3. So with a quadratic, there's 3 different cases. You get one answer that works, one answer that doesn't. What else do you think could happen? Let's see. Yeah?
2 answers that work.
You could have gotten 2 answers that both work. And one more thing that could happen?
No.
Right, no answer works, which means it's a no solution. Okay, let's try another one. Now, notice all these have 3 fractions. If you only had 2, you'd still be able to do it the same way as having 3. It's just easier with 2 than 3, because then you don't have as many denominators to deal with. If I had something like, let's say I had something like that. Sometimes people look at one like that and they get confused because there's not as many fractions. I would just still multiply both sides by x minus 5. You multiply everything by the denominators that's on the left right there. But in this case, there's only one of them. So we are going to do one again, though, that has 2. Okay, first thing you want to check, if you multiply that times that, do we get what's up there? What do you think?
Yeah.
Yeah. So this times that is equal to that. That makes it a little bit easier. What are we going to multiply all 3 fractions by? X times x plus 2. So we have xx plus 2, xx plus 2, xx plus 2. And before you do that out, we're going to cancel whatever we can. What's going to cancel in the first fraction? X, x. What's going to cancel in the second one? X plus 2, x plus 2. And what's going to cancel in the third one? The whole thing. X squared plus 2x. And that is also x squared plus 2x. Okay, so the first one, that is double distributive FOIL. So we're going to multiply all that up. X times x.
X squared.
X squared. X times 2. Okay, I'm just going to put that up here for a second. 2x minus 3x. What's 2x minus 3x?
Negative x.
Negative x. Okay, and then lastly, negative 3 times positive 2. Negative 6. What happens when you distribute positive 3 to what we have left? 3x. And what's on the other side? Negative 6. Okay, and what do we want to get this equal to? Okay. So what would we have to do to get 0 on the right?
Add 6.
Add 6. Add 6. Negative 6 plus 6 is 0. Well, then it also cancels there. Negative 6 plus 6. What do you have on the left side if you combine those like terms?
X squared plus 2x.
X squared plus 2x. Okay, so now we need to solve that. What can you factor out from there?
X squared.
No, not an x squared,
X.
just an x. And what does that leave you with if you factor out an x?
X plus 2.
Leaves you with x plus 2. Now set each of those factors equal to 0. What number would make the first factor 0? 0. And what would make the second factor 0?
-2.
Negative 2. So let's go back up and make sure we can plug those numbers in. Start with 0. Can we plug in 0?
No.
No, why?
The zero's on the denominator.
Of which one?
The first one.
First one and the third one. Right? If you plug the 0 into the first one and the third one, causes you to divide by 0, which means that this answer is what? It's extraneous. Let's try negative 2. What happens if you plug negative 2 in?
It won't work in the middle.
Second and third one.
It won't work in the second one or the third one. So negative 2 also causes you to divide by 0. So what does that mean?
No solution.
There's no solution. Yeah. Both answers in this problem were extraneous. So now you've seen one where one works and one doesn't, and you've seen one where they both don't work. The only one I didn't show you is where they both do work. All right. Any questions on that? Let me make one up, so let's just call that 5A. Let me make one up that's a little simpler because some people get confused with the real simple ones. So you had 3 over x minus 4 equals 8. It's still the same idea. You're going to multiply, actually, let's even make that a fraction, just to. You still end up multiplying everything by the denominators, okay, to make them all cancel out. So what are my two denominators here?
X minus 4 and 5.
So multiply everything by x minus 4 and 5. So x minus 4 and 5, x minus 4 and 5. You just have less fractions to deal with, so it's going to be a quicker problem. What would cancel in the first one? X minus 4, x minus 4. And in the second one? 5 and 5. On the left side, you're left with 3 times 5. 15. And on the right side, 8 times x is 8x. And what's 8 times negative 4? Negative 32. Okay. And now how would you get x by itself there? Plus the 32. And 15 and 32 gives me 47. And my last step?
Divided by 8.
Divide by 8. 47 over 8. That's the answer. So it's actually easier when you have less fractions. But sometimes people get confused, so I just wanted to show you that one. Now, what number would have caused me to divide by 0 in the original problem?
4.
4. Is 47 divided by 8 4? No. 32 divided by 8 is 4. That's 47 divided by 8. So that answer is fine. All So let's finish up the last thing. It's going back to the question about the car, same problem. But they're asking something that's a little different. How is the question phrased a little bit differently this time?
It says less than.
It says less than. When you have less than, that means you're dealing with what? It's not an equation.
Inequality.
It's an inequality, yes. So now we're trying to find out how fast that she needs to drive to complete the trip in less than 2.5 hours. Well, it's still the same idea. You're going to graph the original problem, like we already did. I'm just going to change this to 2.5. So there's the time it takes to do the trip. We're going to have a mark at 2.5. And what do you think I'm going to still find next? Still going to find the intersect. So with an inequality, there really hasn't been anything different yet. What's different is how we write the answer. That's the speed for her to complete the trip in exactly 2.5 hours. But she wants to complete the trip in less than 2.5 hours. So how would you write your final answer? The speed of the car has to be what?
Less than or equal to. Greater than or equal to. Greater than.
Greater than. You can't put less than. Yes, the problem is asking to complete the trip in less than 2.5 hours, but if she drives slower than that speed, she's going to be moving up this curve. That's going to take longer, right? So think of this answer as when you want to complete a trip in a certain time or less, that means you need to drive at a minimum speed. That's her minimum speed. She could go faster, but she can't go slower than that, or she won't complete it in 2.5 hours. And does it say less than and equal, or just less than? It says just less than. So technically that means she needs to go a little faster than that speed. That would get her there in exactly 2.5. So it has to be greater than 34.88. That's the speed. Okay. Any question on that? So as far as solving inequalities, we're going to usually just do it on the calculator. Remember, always check for things that are hidden. Hidden could mean it's off the screen and you can't see it, or it could be on the screen and you need to zoom in to see it better. We will not be solving inequalities algebraically. So we are only going to solve them graphically. So if you see directions in the homework that say use a sign chart, because that's what I had just erased, use a sign chart to solve algebraically, we're not doing that. We're doing it graphically. Okay. All right, well, let's try a few examples. So I think I had just 2 examples. All right, so first, when I type this on the calculator, how many graphs am I going to be drawing on the screen? How many?
3.
And have a thought. How many graphs are we going to be drawing?
One.
2.
Wow.
Right? We're looking for
Because the
2.
exponent is that?
The exponents? Well, we need to type in the exponents. But what's going to go on y1?
What?
Is it like the numerator and denominator are 2 different graphs?
No, they're the same graph.
Okay.
Is
Yeah.
it the one and the other here for graphs?
So what would I type in for y1? Just what?
One.
Just 1.
Okay, we could put the 1 in y1. What about in y2? The other side, yeah. So you have to put one side in y1, and you have to put the other side in y2.
Make it sound so much more complicated.
I was overthinking.
That's a lot of typing to do.
So now, when I type in the left side, what do I need to make sure I put as I type it in? Yeah, there's no parentheses there. You don't need them when you write it, but when you type it, you do. All right. So parentheses 2x squared plus 6x minus 8 divided by, and what do I need when I do the denominator? You need parentheses again. If you don't put them, it won't come out right. Plus 5x minus 3. Okay, so just make sure you type everything in right. And are we looking for where the red one is less than or greater than the blue one?
Less than.
Less than, yeah. So just to make sure we remember which one is which, that's the red one, and that's the blue one, the way I typed it in. If you type it in and you switch Y1 and 2, that's fine. Just keep track of which one is which. So we're basically looking for where the graph is under the horizontal line at 1. Let's do zoom 6 and see what we got. Okay, so so I'm going to set my Ymax just a little higher, so I think we can see something a little better. So there's my line at 1, and then here's the left side, there's the middle, and the right side. You still can't see what I was going for that well, but that's fine. Okay. Which part of this graph does it look like is never less than 1? And we can basically ignore it.
The first part?
Yeah. Looks like, wait, which part?
The like the top part?
Yeah, that part in the middle. I'm not seeing anything there that goes below the blue line, so we can ignore that part. Let's look at the left part. Okay. It looks like it's under the blue line. That's what we want. But I want to go to my table, and let's make sure that it stays under the blue line if we keep heading to the left. Let's go to our table. Let's try -10. Is that still, look at the red. Is that still under 1?
Yeah.
Yeah.
All right, let's go further. Let's go -50. All right, it's a little bigger, but is it still under 1?
Yeah.
Yep. Let's go like -5,000. Is that still under 1?
Yeah.
Yes, it is. So we went all the way to -5,000. It's still under 1. I would say it's going to stay under 1 forever. If you've gone to -5,000 and it hasn't gone above it, it's probably not going to. Okay. So how low? Let's call this interval 1. This will be 2, which we don't even need, and 3. How far to the left does it look like interval 1 is going to go? Yeah, just going to keep going down forever. Now, does interval 1, look at the red graph, does it keep going to the right forever?
No.
No, all of a sudden it stops right at that number. What number does it look like it stops at?
-3.
-3. Okay, I'm going to make that number so it's easy to find. If you graph it, it's not going to be something you have to calculate, and it is -3 because I got an error. Can I include or not include -3? Can't include it. So that's the first part, where the red graph is under the blue one. Everything in section 1. That's what I just described. Section 2, it's never under the blue one. Now, let's look at section 3. Let's check the same thing. If we head to the right, we need to make sure that it stays under the blue line the whole time. And the blue line is at what number?
1.
1. Right. So let's check like 15. Am I under the number 1? No, I crossed it. So it's crossing the blue line somewhere in here. So there's a point where that red line is no longer under the blue one. We need to find that. So we could check 3. All right, that's still under. 4 is still under. 5, it looks exact, so we got lucky. We know it's 5, but we'll pretend we don't know that. We go to 6, and now we're above it. So at some point between 4 and 6, it went from being under 1 to above 1. We need to know when it hit 1. So how can I calculate where it hit 1? Yep.
Intersect.
Yeah, we'll calculate the intersect, and it might not always be a nice number like 5. So let's move our cursor over. That's close enough, it'll find it. And it says it intersects at 5. So for this graph, you do not want to go past that dotted line. If you do, the red one goes above. We want to know when the red one is below. Okay, so look at section 3. What's the highest we can go in section 3 and stay under the blue line? So what number would you put right there?
On the right side would be 5.
5, yep. So we can go right up to, but not including 5. And does it look like section 3 goes to the left forever?
No.
No. There's another vertical asymptote that it's hitting right there. Where do you think that number is?
Like a half.
A half. I told you I'd make it easy to find, so let's just try 0.5. We got an error. Yep. So it is 0.5. So can we include or not include that?
Not included.
Can never include an asymptote. That's where you are less than 1. Now, let's say it said that, less than or equal to 1. We almost have the same answer. There's one thing there that would change. Only one symbol.
The right bracket.
All the way on the right, this would become a bracket. You can't put a bracket on the 0.5 or the 3, because those are asymptotes. You can never include an asymptote. You also can't put a bracket on negative infinity, because you can't reach negative infinity. The only thing that would be able to include is where they're exactly equal, and that would be right at 5. So if it said less than or equal to, all you do is make that symbol a bracket. That's the only thing that would change. Okay. Any questions on that? All right, so that finishes up solving rational functions. And that's the last day we spend on those. Tomorrow and Wednesday, we're going to look at radical functions. Okay. So those are ones with like square roots in them. And we do the same thing we did here. We're going to sketch them, not in as much detail as those, and they're actually a lot easier to sketch than things like that. And we're going to solve them. So we'll do both over Tuesday and Wednesday. Okay. So that's the homework for tonight on page 244. Okay, 1 through 13 is just odds. And then it's 20, 22, 24, 28, and 31. Okay, so we'll take a look at that tomorrow, and then we'll start our last section for the week tomorrow, and review day on Thursday.